So this video is going to be a preamble to my pushover video. I realized that I was kind of getting into a lot of theory at the start, and so I wanted to separate that out into a different video. In this video, I'm going to overview two of the most common integrator types in OpenSees for static analyses, and those being the load control algorithm and the displacement control algorithm. So let's just pull up Wikipedia. You're probably aware of these commands. The integrator objects do quite a few things, but for us, the most important thing that they do is they'll change how, they'll specify how the program goes from time step 1 to time step 2. And as I mentioned, we'll look at the load control command and the displacement control command. To understand why this is significant, let's just look at a simple, get out of here text. Okay, let's look at our cantilever. Let's just say we apply a load to the top of it like such. Now, we know from prior videos or maybe from experience, if this is, say, your P0 that we're applying to the cantilever, how this force changes with respect to time will vary based on the time series. So we can think of our P as a function of time. So P at every time step will equal some, we'll call this a phi factor, as a function of that time step multiplied by the original reference load. So in this case, P0. And we can think of it like this. If we look at our graph, phi as a function of time, the time series that we specify for our loads is what tells phi how to change. So if we had the constant time series, phi is constant with respect to time, linear, it's linear with respect to time, it should be pretty intuitive. However, now what we're looking at is how these time steps actually change. So if we have some initial time step t1 and some other time step t2, the integrator command will help us get from T1 to T2, or rather it's the rule that lets us choose T2 when we have T1. We can think of at every time step how we get to the next time step in terms of a similar equation. We can say T2 will equal to some lambda times some change in the time step plus time 1. So really, this is what we're thinking of when we use the integrator to go from one time step to another time step. We're thinking about changing this lambda. Another way of writing this might be like t2 or t whatever, tn will equal lambda times some sort of reference time. But let's just use the top equation, and specifically I'll just set delta t equal to 1, so we're left with this equation just for simplicity. Okay, so like I mentioned, the integrator command is going to help us choose our lambda factor that will take us to our next time step. Overviewing the load control command, we'll start here because I think the load control is the simplest. The name, if you know nonlinear theory, there is some precedent for the name load control, but this might seem a little counterintuitive, because really it has nothing to do with the forces in our model. The way that the load control algorithm works is we change lambda in some sort of fixed amount. So lambda will be a constant. We can specify some bounds on lambda. So it can change around within a certain range. If you look at the integrator command, we specify the initial amount, and then we also specify like the minimum amount and the maximum amount. So it will change. There are some rules that OpenSees has, like if your analysis isn't converging, it might choose, or if it's taking a long time to converge, it might play around with the step size a little bit. But unless you've specified this sort of range, which we don't need to do, and in fact it might be preferable not to do just for simplicity, the lambda will just be a constant. So as we go from T1 to T2 to, let's say, T3 over here, we're just changing by this constant amount, which is lambda. And again, it's a little bit more complicated than this, but unless we specify some additional controls, this is what it will be like for the load control. So if you think of how the forces are scaling, the forces will move by some sort of constant amount. And we'll look at a diagram now. Let's say we take our cantilever and it has a nonlinear property. So say something like this, where this is the load applied and this is the displacement at the top of the cantilever. Like that. Let's think of what will happen if we use a load control scheme with our initial P0. The loads that we'll end up getting will look something like this. We'll have P0, 2 P0, 3 P0, etc. So as we go from time step to time step, because we have a linear time series, it will change by a fixed amount. So P0 in our model is changing by a fixed amount. So this load control scheme is a pretty straightforward way of going about solving the algorithm. If you have a linear command, we just linearly increase the load. We linearly increase the time steps with the linearly increasing load from the time series. And as we solve it, we'll end up with getting these equilibrium points. So if we think of this being the real equilibrium path of our cantilever, we'll end up getting these 3 points. However, as you might imagine, we can end up running into a problem if we were to, say, move to our 4th time step now. So if we were to try T4 and we ended up with this load, 4 P0 up here, OpenSees will get really mad at us because we have specified a load that the equilibrium path can't possibly reach. So it will try and do all these iterations and it will ultimately fail because our structure just is incapable of reaching this force. So this is a feature of using the load control algorithm with forces. We can end up in a situation where we can't actually capture the deterioration of the curve. So if we think of this curve over here, with our load control algorithm, we can't actually get past the peak point. So if our curve looked something like that, if it looked something like this, we can analyze and find every point using our load control algorithm and forces up until we reach this very peak point where the slope becomes 0. And then ultimately the algorithm will fail at this point for exactly the reason that I specified further. Because if we try and scale the load any larger, we just won't be able to, there's just no more forces. So any force past the peak force, we will end up with a failure. So this is for the load control of forces, it's a fairly substantial limitation. You might wonder why on earth you might want to use the load control with forces if you might end up with this situation where we can't actually capture the deterioration. Well, it's still a fairly useful command because I think it's pretty straightforward. It's really easy to understand what's going on. Like if you specify a load step, it's just conceptually easy to understand. Okay, I know exactly how much my force is changing from time step to time step. It's all really clear. And of course, for some situations, we might not need to get the deterioration. One way that we could go about, if we want to get the deterioration of the curve, we could, instead of specifying a force up here, we could instead apply a displacement. So if we, and you know what, let's just pin this bad boy. Yeah, so we could instead specify some u0 factor. And then if we think of what's going on, our time step is still changing linearly. But instead of having the forces change like this, now we're having the displacement change. So if we look at what that will be like, so as I struggle to erase everything, if we look at what that will be like, we will instead be changing the u value. So initially we'll have u0, 2 u0, 3 u0, etc. And in approaching the problem this way, we can actually capture the deterioration of the curve. So using a load control algorithm with a forced displacement, you can capture the deterioration of your structure. I know that's a little counterintuitive, but like I said, the name load control doesn't have anything to do with the actual forces that you apply to the structure, and is a bit of a misnomer that way. So if you're new, just know that you can actually apply forced displacements with your load control algorithm. That's totally fine. One challenge with doing this, however, is it doesn't necessarily extrapolate well to all situations. And when I say doing this, I mean applying displacements to the model. One challenging situation that we can get into is because we're forcing a certain displacement, we may lose information about the model, or we may make inaccurate predictions as the load increases. And let's just think of, I'll put this to an example because it may not be clear just talking about it. Also, I love how I have this gigantic space and we're only using a tiny part of it, but I guess that's what we're doing for now. So let's say we're applying multiple force displacements. Like maybe this is a building and we're applying displacements at each floor. So we'll say u0, u1, u2. And so these are the initial displacements that we're applying at different points in our structure. However, this is all well and good, but let's now say that for whatever reason, our structure will end up yielding right here at this point. If we use if we're using these original displacements, we'll actually not be able to see that yielding properly. Because if you think of what's happening, if the cantilever yields at this point, you should see some displacement like this. Like we should see concentrations locally of rotation. And so if we were to constrain the structure, such that the displacements are in this initial shape, we wouldn't actually be able to capture the yielded shape of the structure. So that is, even though we can use this in some situations to capture deterioration, is definitely not going to be the method of choice for all scenarios. Specifically, applying displacements with load control won't be the method of choice for all scenarios. For exactly the reason that I've said, if we have a change such that the displacement shape is different than the original one, we're not going to be able to capture that because we're forcing the structure to have this initial displacement. So just know for some circumstances you might not want to use you might not want to use the load control algorithm with displacements. So if you're in that scenario, what you can do, however, is we can use the displacement control. So that one's over here. So you might notice when you're looking at this command, so in the load control command, we have just the increment. That controls the number of iterations, typically not that important, and then the minimum and maximum increment. In displacement control, we have these additional commands, the node tag and the degree of freedom. So the way that the displacement control algorithm works, so before in load control, lambda was it was a value we told the program what lambda to use. However, in displacement control, OpenSees will actually figure out what lambda to use such that we get a certain displacement. And to make this ultra clear, hopefully, think of the first situation that we had where we're applying a load here, P naught, and we'll be looking at the displacements also at that top node. So to use displacement control, we would specify the node to use. So in this case, we would use the top node and the degree of freedom. So because we're applying load in this direction, we're concerned with the first degree of freedom, which is in the x direction. And then we'll specify displacement. So we'll maybe say we want 1 centimeter at our control node in that degree of freedom. Then what OpenSees will do is it will find out what lambda will give us this displacement, and then it will apply that much force. So if say 1.75 of our initial force gives us this displacement, then the first lambda 1 will equal 1. It will equal whatever gives us the assigned displacement. So this is a pretty flexible method. We can actually capture the deterioration of the structure using this method and applying forces. So it is nice in that way. I will say, however, it is also one drawback is that we kind of lose transparency on how the loads are changing. Because we tell OpenSees, okay, I want this displacement, just do whatever to find that displacement, which I find can be a little opaque. Sometimes I like to be explicitly controlling how my load step changes. But of course, for all scenarios, that isn't necessarily the case. And there are definitely going to be some circumstances where you really want to use the displacement control algorithm with forces. So it can be quite flexible that way. I will note one challenge that you can end up with this method is, let's say we have a really strange curve. Let's say our load curve looks something like this. In this case, displacement control won't actually be able to get past this point. Or it won't be able to capture this particular region of the curve. I'm now speaking a little, I'm not entirely sure what would happen because truthfully, I've never had to analyze a curve like this. But speculating, I'm pretty sure it would just pick up this point over here and then continue along the curve. So instead of capturing this, it would all of a sudden jump. You'd have like a big line and it would jump. So yeah, we won't actually be able to capture this sort of motion of our curve. However, I think for most people, this isn't really something you have to worry about. This is like, for most structures, this is a really strange sort of curve. So unless you're working with some sort of like polymer or something, you probably aren't going to have to deal with that. And if you are, then I'm truly sorry. If you do need the ability to capture some weird funky curve like this, you won't be able to use either the load control or the displacement control. You'll have to use the arc length control, which I will not get into. If you're doing anything typical for structures, you do not need to use arc length. So this with this in mind, well, I'll just like quickly summarize the techniques that I talked about. How do we how do we draw text in PowerPoint? Please, text box. Okay. So when we're trying to apply some of these lateral forces to our structure, the techniques we can use are load control with forces. We can also use the load control with displacement, and then we can use displacement control with forces. So if you're doing a pushover, you're going to want to use one of these. Like I said, load control with forces is the most simple. However, you can end up with problems where you can't get past the peak. Load control with displacement, we can capture degradation, but you might end up in a situation where you're not able to capture, say, the new shape of your structure if you're applying loads, if you're applying displacements in multiple locations. And then we have the displacement control with forces, which is pretty powerful, but again, we kind of hand over some of our control over how the load changes to OpenSees. So it's a little bit more opaque and it can be a little bit more difficult to debug. Okay, so hopefully this was useful. I kind of wanted to get this out of the way in a separate video before we went into the actual pushover process. In the pushover video that I'm going to do on this model up here, we'll use each of these 3 techniques to apply the pushover.